And I'm sharing. Let me make sure that I'm sharing this thing. There you go. Okay. So we've been talking about separation of variables. And last time we did that exercise of that box, well, of that square cavity, and we were trying to find out, okay, given a specific boundary conditions, and all this is at ground, given a specific boundary conditions, what will be this function of the electric potential? Okay, knowing that if I can find the electric potential, then I can find the electric field, I can have the electric displacement, and et cetera, et cetera, et cetera. So I want to go a little bit of how you solve this a little bit more. Okay, we did all the mechanics last time. We come up with the solution. So I'm gonna do a very similar problem, and there's some issue of how you apply this separation of variables that can be a little bit tricky. So it's gonna be a very similar problem. X, Y, I have Z. And I'm gonna assume that I have two plates. One plate is gonna be here, and they're infinite plates. And the other one is gonna be at a height A. Something like this. Okay, and they're gonna be, oh, well, they're gonna be this wall over here. That's the one that's gonna be at an electric potential B naught, and these two are gonna be zero. They're gonna be grounded. Sorry, this is just B. Okay, does the drawing make sense? Okay, so we're not going to come up to the final solution of the electric potential. We're going to leave that as a homework, but I'm going to try to work all the way until we start solving all the boundary conditions. Okay, so one of the main issues with this kind of problems is finding those boundary conditions, is finding what are the conditions that we need to solve. So this problem is a little bit tricky because it is closed on one side, it's infinite in the Z direction, but it's open on one end, okay? So I want you to take a minute and write down the boundary conditions, okay? I think the boundary conditions for these three plates should be relatively easy. The fourth one is the one that's a little bit tricky, okay? So take a minute and write down just those boundary conditions.
Just keep running.
You're not cold.
You're
not cold.
No.
I don't think so. Yeah, Nick, you got it?
Might have one.
Which one you got?
When X equals 0, B equals 0.
So when X equals 0, you're talking about this plate. So B is going to be equals to B naught when X equals 0. Look at your axis. Yeah?
Yeah.
Yeah. McKenna, you have any boundary? Nico? What will be the voltage when Y equals 0? Yeah, so B will be 0 at Y equals 0. What will be the location of this plate? Makina? The top plate, what will be the location? What's the value of Y for this plate? A. So what will be B when Y equals A? No, that's just B. So here we'll have that one. Okay, so these are the three boundary conditions that basically are these three places that we know. Now, the last final condition will be on this opening that we have on the right side. Now, we have the electric potential on one plate. And if you imagine, for example, if you have a point charge and you're getting closer and closer to that point charge, the electric potential is going to increase. And as you move away, that electric potential is going to decrease. If you are really, really, really far away, you can imagine that the electric potential is almost going to be 0. So we can say something similar here. We can say, okay, the electric potential is going to get closer to 0 when X goes to infinity. Okay, and this will be our final boundary condition. Okay, make sense? Yeah. Okay, so this is pretty much the first step that you need to do in this kind of problem. Just identify what are the boundary conditions, what are going to be the equation that you're going to solve. Now, when you apply separation of variables, and this is the tricky part, okay, we're going to say that our function of the electric potential is just going to be the product of two functions, one that's only going to depend on X and one is only going to depend on Y. And then we can apply Laplacian on this equation. Okay, now I'm going to apply this Laplacian to this factor, and then I'm going to get y of y, actually, y of dx plus x dy equals 0. This is pretty much what we did last time, dividing by v. Oops, by v, then I'm going to end up with 1 over x is 1 over y dy. Okay? Now, what we saw last time is that the only way we can solve this equation if we're taking double derivative of a function that only depends on x, and we take the double derivative of a function that only depends on y, and we add them together, and those are equals to 0. The only way that can happen is that if these are equals to constants. Okay, so all these have to be equal to a constant. So we can actually add them together and be 0. Okay, and then last time, well, we said, okay, let's make K1 negative and then K2 is going to be positive, and then we solve. But we never show, I never show, how do I know that this is negative, or how do I know that this is positive? Why is not the other way around? So this is just a way to figure out how you pick, or how can you define which one is going to be positive and which one is going to be negative. It's an additional step at the beginning of solving these kind of problems, but it can solve you a lot of headaches that if you don't do it, then you can end it to the end and it's like, holy crap, I cannot solve it. Okay. So I'm gonna go and start working with the y direction just because I have these two boundary conditions here. Okay. So I'm gonna have one of y equals to K1. Okay, now K1 can have three different values. K1 can be less than 0, can be 0, or can be bigger than 0. Okay, so I'm gonna go and do the one that is easier. I'm gonna do, okay, what happens when K1 is equal to 0? So when K1 is equal to 0, then this differential equation gets simplified to something like that. Okay, I integrate twice, or I integrate once, and I'm gonna get equals to a second time, and I'm gonna get ay plus b. Okay. Now, I have this form, and I'm gonna look at my boundary conditions. Okay, so I'm gonna look at my boundary condition, and I know that v is gonna be equals to 0 when y is equals to 0 and b equals to 0 at y equals a. Okay, I'm gonna look at those two boundary conditions. So I'm gonna look at the first one. Oh, actually, you guys do that. Solve for a and b using these two boundary conditions. So what will be, or what will a, what values do I need to have in order to make this boundary condition true? Remember that b is a product of x of y. So if I want b to be 0, if I make y 0, then that will be true. Okay. So apply these two boundary conditions here. Nick, I have one more gun.
I'm good. I brought my own.
Okay, you need it?
No, not yet.
Okay. Makia? Not yet? Okay. I give them gun because they fall asleep.
Oh, good stuff. It was a long night for me last night.
And Nico doesn't eat gum, so that's why it doesn't operate.
Well, 6 a.m. practice.
You have 6 a.m. practice,
Yes.
and then class
Yes.
at 7.
8:30.
8:30.
My 8:30 class was online today. That was pretty nice.
Okay.
Professor Doherty, her daughter-in-law was giving birth, so she
Oh,
was
wow.
babysitting.
Oh,
Congratulations to her. That's cool.
Yeah,
I didn't know that.
it was weird to have it. I would not want Spanish online
Yeah.
because everyone, like, she'd be like, "All right, repeat after me," and then it's just like 20 people turning on their mic and all trying to say the same Spanish word, and it just came out as brr.
I can imagine this movie awful. So when y equals 0, then I'm gonna have that y is gonna be equals to a0 plus b, right? So if I want to make y 0, so this function also goes to 0, then that means that b is gonna be equals to 0. Okay. Now, if I do this, the other function, when the other boundary condition, when y equals a, I'm going to have a of y, and I need this to be 0. So y is not 0, So the only way is to A equals 0. Okay, so that means that y equals, I don't have any function y, it's just nothing. And if this is nothing, then I don't have any electric potential. So this cannot be my solution. K cannot be 0 because then y wouldn't exist. And that would make no sense. Okay? It's tricky. Okay, so from all these three solutions, I just discard the first one. Now, should we do? Now, let's say I'm going to look for the second one. Let's say that K1 is bigger than 0. Okay, so then this equation, this differential equation will be 1 over y equals to K. And I know that K is going to be a positive number. And this one is a differential equation. It has a specific solution. And I know that this one, and I need to double check, this is going to have AE to the KY plus BE to the minus KY. Yeah. Okay, and I'm going to do exactly the same. I'm going to apply these to boundary conditions. And I'm going to try to make y equals to 0. So when y equals 0, is this one? Yeah. When y equals 0, I'm going to have a e to the 0 plus b e to the 0. So that implies that a has to be equals to minus b. Okay, it could happen. Nothing strikes right now that couldn't happen. So okay, we're gonna keep working. The other boundary condition is that will be when y equals a. Okay, so then my function using this condition that I just found is gonna be that y will be a to k a minus a e to the minus k a. Okay, factoring this a, we're going to have a e to the k a minus e to the minus k a. Okay, and again, what I want is for these things to be 0. So there's one solution, a to be 0. And if we make a 0, then y is going to be 0, and then we got the same case as before. The other ones will be, would this be possible to be 0? Do we have a particular value of k and a that can be 0? So this is a sine hyperbolic function. So this is the same as 2 sine hyperbolic of ka. Okay, and sine hyperbolic has this, the only way that a sine, or the only point in which a sine hyperbolic is equal to 0 is when the argument is equal to 0. So that means that k and a will have to, k or a have to be 0. And if k is 0, then we go back to our first case, which we already established that is nonsense. If a cannot be 0 because that's a physical position of our plates. So it turns out that this can never be 0. So a will have to be 0, and we got to the same point. If a and b, if a is 0, b will be 0, and then we don't have a function. So the only solution that we have is that K1 has to be negative. And if that's the case, then K2 will have to be positive. And that way we establish, we can solve now our differential equations. Yeah? Make sense? So how would our functions look? So, okay, so now I have these two equations. I know that this guy is going to be negative, and this guy has to be positive. I think oh, this K2 has to be negative. This K1 has to be positive. I think I mislabeled it earlier. So now we have 1 over X equals K, and K will be positive. So I will have that this will have the shape AE to the KX plus BE to the minus KX. And then for Y, that will be negative. And this one has a particular shape that is C sine of KY plus D cosine KY. And then I can find my BXY. Well, it's a general shape. That will be AEKX plus B minus KX. We're not even close to solve this problem, but at least we know the general shape, and you won't go through what happened to me last time that I did the whole problem and then I realized, oh crap, K was supposed to be negative. Okay, makes sense? It's an additional step, but it's better than guessing. Okay. Any questions so far? Okay, so we're not gonna solve it all, but try to apply. We're gonna try to find these boundary conditions. Some of these constants, okay? So what I want you to do, and there is, again, to solve these constants, these are the ones that we need to solve for, we need to apply the boundary conditions, okay? So I'm gonna apply, and this is another thing that you get by a little bit by experience. Some boundary conditions are easy to apply. Some of them are not that easy. So for example, I'm gonna say, for my boundary conditions, I know, and let me get back to them. One of my boundary conditions is that V naught is gonna be 0 when Y equals 0. Okay, so V is gonna be 0 when Y equals 0. Okay, so I'm gonna have 0 equals AKX plus B minus KX. And then I have C sine of 0, the Y 0, that will be 0, plus D cosine of 0. Okay, so cosine of 0 will be 1, sine of 0 is 0. So the only way this function can be 0 is if D equals 0. Okay, so we solve one of those variables. Okay, make sense? I'm gonna do another boundary condition, and that's gonna be that V equals 0 when X goes to infinity. Okay? It's okay, Nick. It's okay. We're almost there. Okay, so
Almost there.
we're almost there. So,
It's almost over.
oh no, we're not even close. So we're gonna have A.
No.
I know I'm gonna just write it like that. I know it's not correct, but just and b e to minus k, and this is infinity. I guess I should do the limit when x equals close to infinity, blah blah, plus c sine of ky. Okay. Now e to the minus infinity, that's 0. So this is gonna go to 0. E to some very large number is going to be different than 0. So the only way that this can be 0 if it's a is equals to 0. So that will give us our second boundary condition. So now b of x, y, going to have this shape, e kx c sine
B,
ky. What?
B, the
Yes,
Just figured out that.
there you go. I'm going to rewrite this. b e to the minus ky c sine of ky.
why not X?
X.
Friday.
It's Friday, and Dr. Jensen makes me nervous. Okay. Now, what we need to do is now we're going to apply the third boundary conditions to find an expression for k. So b is going to be equals b0 when y equals a. So that will be 0 will be ve minus kx c sine of ka. Oops. Okay. So we want sine ka to be equals to 0. And that will imply that ka will be a multiple of pi. So k will be m pi over a. And m can be integer values. Okay, so now we can rewrite that v xy is going to be c e to the minus m pi a x sine of m p a y. And this constant, this c will be just a times my renal c.
Not B.
B, my B times C. Yeah, the product of these other two constants. These two constants. So this product of these two constants, I'm just combining them in that single constant over here. Okay.
I was not taking reason nothing. I was just thinking through all the variables we're already using here. And it's like,
So we still need to find this constant to find the final solution. So we still need to apply the last of our boundary conditions. So the last of the boundary conditions is that V is going to be equals to V naught when X equals 0. Okay, now the problem is that we're going to have now an M number of solutions. So V naught is going to be equals to the sum of Cm sine of M pi over A y to infinity, M's. Okay, and this is where we were when we were not yet last class. Okay, so the last boundary condition is basically to find this factor Cm. Okay, and that's what we were looking at the orthogonality, and we were looking at the Fourier series of this thing. So you can multiply this by a orthogonal function. So in this case, will be sine of n pi over ay. Okay, and then you integrate from 0 to a and dy. And then you can guarantee that because these functions are orthogonal to each other, then you're only going to keep the solutions when m equals m. Okay. Yeah. That's going to be homework. That's going to be your homework. Just finishing this problem and find that expression for Cm, and then find the final solution for Vx or y. Yeah. Write it down. There's a couple of more steps. I think we did the heavy lifting now.
It'll take them just about half a class.
Yeah, so we're getting faster. Yeah, we were working on this, and it took forever.
These are slow problems. It's a very general broad technique, but it's slow.
And we're not doing spherical now yet.
Yeah.
We're gonna skip over.
Yeah, can we skip
sphere.
that?
Best I can do is cylindrical.
So useful.
It is useful, yeah.
I think I've seen some books that do spherical in the text, and then the cylindrical stuff is all just homework. You would derive the cylindrical version in homework.
This book, it only shows you the separation of the variables, how you separate the variables, how you apply the Laplacian, but they don't do the problem.
Oh.
They only do problems on rectangulars. And I think, I don't know, I need to double check. I think there's a couple of homeworks involving spherical, but it's kind of weird. And Griffith doesn't do cylindricals. He just goes to sphericals, and that's it.
And we all make choices.
That was a weird kid in class in math. I looked away when we were having that whole the police chase out in front of the school. Before that happened, I got a notification from my group chat. And I looked down at my phone. I looked back up at the board for linear algebra, and she had wrote Laplace's on the board, and I was like,
again. Okay. Did you guys got it?
Yeah.
Yeah. Okay. So one of the things we're going to take a break from this, and what I want to show you is a software that basically helps you solve these kind of equations. It's oh, here it is. The software is called COMSOL Multiphysics, and what it does is that it kind of finds links between different domains of physics. So, for example, let's say that you have to design a boilerplate or a boiler, a container of gas, and you know that the gas is going to be under a lot of pressure and really high temperature. Okay, so there is a part of physics simulation that you want to, for example, look at what will be the heat exchange with the exterior. You don't want that plate to lose a lot of heat. But also is the heat and the pressure is also going to change the physical properties of the metal. If you heat it too much, the metal is going to become a little bit weak. So you can see how that pressure and how that heat will affect the metal and if it's going to deform. For my research, what I do a lot, for example, is mirrors when especially solar collectors, you have spherical mirrors and they used to focus light in a specific point. But if you receive a lot of sunlight, then it's metal, and it's gonna deform, and if it deforms, it's gonna change the focal point. So now instead of pointing in one place, it's gonna be pointing in a different place. So that kind of, you're combining physics with thermal optics and mechanical properties and stuff like that. But you can also do electrostatic problems with this software. So what I show you is a little bit of the problems that we've been doing so far and what it will take to do it in this kind of simulation. So I'm gonna go a little bit quick. So we're gonna be working in 2 dimensions. And we're gonna be working with electrostatics. So we're just gonna work with electrostatics problems. And the kind of problems that we're doing right now is stationary problems. We just have a particular value of electric potential or charges distribution, and that doesn't change with time. So I'm just gonna pick those. Okay, and I'm gonna have this menu over here that is looks kind of daunting at the beginning. And what we have here is all the things that I need to define on my program. So I need to set up a geometry, I need to pick up the materials, and I need to pick the conditions that I need to satisfy for my problem. So I'm gonna do something very simple, and I'm gonna say I want to have a charge, a metallic sphere with a charge, and I want to look the electric field outside. So I'm gonna add my geometry. I'm gonna add a square, and I'll show you why I want to add the square. And I'm gonna do 1 meter. And then I'm gonna add my charge. It's gonna be a sphere, and I'm gonna make a small sphere. So I'm gonna say, 5 centimeters. Oops. I'm gonna center this thing. There you go. Okay, so one of the things with this software, okay, this is the thing that's gonna be charged. This is the thing that I want to look at. But if I only pick this, it's only gonna solve for the electric field in the sphere, which doesn't make any sense because I want to see the electric field everywhere, inside the sphere and outside the sphere. So I need to give the software, okay, calculate the electric field also here. Okay, this is gonna be my air if you want. Okay, so I want to see the electric field also in the field. So now I'm gonna pick the materials. And I'm gonna pick 2 materials. So I'm gonna pick air. Okay, so I'm gonna say all this is gonna be air. And I'm gonna pick copper. There it goes. Okay, and copper is gonna be this thing over here. Okay, so I have 2 materials. It's a sphere of copper surrounded by air. And I can change the air, and I can say, well, I want it to be quartz, or I want it to be Teflon, or I want it to be water, or something else. And now this is the cool part.
Copper surrounded by more copper.
Copper surrounded by more copper. And here's the part that is that's always kind of tricky. It's okay, I have conditions that I want for my problem. So this one is kind of simple. Here are the different options that I have. And what I want to do, I'm gonna have an electric potential. So I'm gonna say that these boundaries, all these, are gonna be at 100 volts. Okay, and the rest here, they are 0 volts. I'm gonna be a little more specific, and I'm gonna say, okay, you know what? I want this, the outside, to be ground. So all these are gonna be ground. Okay. With this particular simulation, doesn't affect much, but when you are simulating radio waves, if you don't ground your boundaries, then the wave kind of bounces back, and then you get different results. We want in our simulations, we are assuming that these things are at infinity. So we just want to see what is the radiation very, very far away. So if we don't cut them with ground, we're gonna have a reflection back. So those are kind of things that are kind of tricky. We're gonna do a mesh. Okay. So the way this software works is what's called a finite element method. And basically what it does is that it's gonna take each one of these triangles represent a set of equations. So it's gonna look at the boundaries and it's gonna solve Gauss equation. I'll show you where it is. So here the equation. These are the questions that is being solved. And now you can understand what are these equations, right? So these are the two equations that have been solved. So each one of these triangles represent those equations. And it's gonna solve one triangle at a time. And then the output of this triangle is gonna be the input of the triangles around it. And it just goes by that. Just do one triangle and then the neighbors, and then keep going, keep going, keep going. The more triangles, the finer your mesh is, the better your result. But also, the most intense the computation is going to be. Okay. And then you compute.
That would take me years.
And there you go. The electric field, the electric potential.
Can't even see the mesh.
And the mesh disappears. It's going to show you in the result. But yeah, it's so fine right now that you don't see the. We're going to look at the surface. And this is the expression right now that I'm plotting, just the value of electric potential anywhere. So if I click at any point, you can see the coordinates and the value of the electric potential at that point. So if I put somewhere in the center, well, I know that in the center is going to be 100 volts. If I move away, it's going to start decreasing. Okay, I can do a line like that, and it will show me the electric potential, and then you can see inside the circle, inside my sphere, it's going to be 100. As I move away, it disappears, and when I reach the edges of my limits, it's going to be 0. I can plot. So, for example, these are the variables that I can plot. So here's the electrostatic, and let's say that I want to plot the electric field. And I will show me the electric field. Okay. Makes sense? Now let's do let's do the problem that we did Monday. And the problem that we did Monday was the cavity, right? So I'm gonna do a rectangle, and I'm gonna say that the width, I'm gonna say that it's 2, and I'm gonna center. Okay. I'm gonna add my materials. I think we said that it was air. Yeah, so everything is air. And I'm gonna add my boundary conditions. So ground, I'm gonna say this is ground, this is ground, this is ground. And then the electric potential. We're gonna say that that's 100 volts. Do the mesh. Oh, I didn't do the mesh. I'm gonna make a finer mesh. Okay, so you remember that graph that I showed you using MATLAB? And then we will switch it. So this is it. It's the same. This is the electric potential. We have a maximum value here on the plate. There's 100 volts. And then as I move closer, I'm gonna be going to 0 volts. And the cool thing is that I can change my conditions and say, okay, now I'm gonna add these two. I'm gonna be at 100 volts. And then I can compute it again and then look at the electric potential. So a little bit faster than what we've been doing.
Just a tad.
Just a tad.
faster than us.
So you can do pretty cool simulations with this software. Let me see.
What would be the difference if you did a different material? Just a different layout, like.
Sorry.
That'd be different.
What?
Like that definitely be different.
Yeah.
Well, I pick
If you change the material.
inside.
People using like concrete instead of.
Yeah, use concrete.
Concrete's gonna be similar, but I wonder.
Yeah,
On the inside though?
Yeah, and it'll be a dielectric.
The electrics. Yeah. So let's say you want to change the electric. Let me see. What would be a good one?
Brick.
Acrylic. So when you look at acrylic, let me see. This one doesn't have. So what? This is a little bit of the limitations of this software. You don't see.
okay, you have the value.
So the value that we care when we're working with these kind of simulations is the electric permittivity. Okay, but this software is being used for people that are in mechanics, civil engineering, whatever. So they may have acrylic plastic in terms of construction or part of the mechanical properties, not necessarily their electrical properties. So in this case, we will need to add the electric permittivity, the relative permittivity, so we can use this one. So let me see. Quartz.
Oh, that is.
So here we have a relative permittivity of 4.2. Okay, so what will happen? What will happen if you have this cavity and then you put a different dielectric inside? What happened to the electric field? What happened to the electric potential?
Larger permittivity, decrease it.
So we will expect that. We have that.
We were working with something that just had like a 1.5, right?
Yeah.
There's like,
So
4.2.
yeah, so go.
we have Gauss law, and then we have expressed in terms of the electric field, then this electric permittivity is going to affect the magnitude of our electric field, right?
Yeah.
So I didn't record the electric field before, and let me see if I can show you. And so right now we're looking at electric potential, electric field. I didn't record it, so we won't be able to see. Oops.
Oh, ooh.
Yeah.
Okay. That was interesting.
Not exactly what I expected, but.
So the colors are like relative, right, to the
Yeah.
scale of the whole thing.
Yeah.
And the issue is just, you've got those corners where you have a discontinuous potential.
Yep.
So near those corners, it's gonna be ridiculously high field because you've got,
Yeah, you have to the
Jeez.
third.
That scale's ridiculous. 10 to the third, 2.5.
Yeah.
Yeah. So it has limitations. I mean, it's not a perfect software, and And one of the things that you need to know what to expect, not to trust the software completely blind. Let me see if I can show you.
A lot of common sense, basically. Let's go into it.
Yeah.
Pay attention to your scale, apparently.
Dude, why does it think that's a good scale?
So, for example, this is the quadrupole, which if you try to do the simulations, or if you try to do the analytical results, you end up also with a series. I think we did it with the quadrupole. And you usually, when you do the analytical solution, you just take a couple of terms, and here you can simulate. Well, you can do a simulation, and then you can change the distance quantities, and you can get a better idea what it is. The thing that I do a lot with this thing, let me see if I can find it.
Do you folks keep track of files these days? Do you like put files in directories and all that kind of thing?
Yeah.
I try to, but a lot of times they'll just end up being like, all right, I have a million different scans, PDFs or whatever, of like homework and whatever else. I'm just like, yeah.
I read an article just the other day talking about how people who've grown up in the era of having, apps and, phones and things, have the keeping track of files. Younger students today just don't even have that model in their head of file systems and folders and things.
On Google Drive, my drive is very well organized, but everywhere else.
Yeah.
My folder or whatever, that like same thing that you have down in that in your hotbar or whatever. Mine's pretty organized. I still have my all my scans from like freshman year.
Nice.
I'm over the each class section.
Yeah.
For those scans, I also delete them after I submit them most of the time because I have it on I have a notebook.
So
Yeah.
just to finish, so this is a simulation of an antenna array. So you have this plus sign that you have over here, and this is made of a semiconductor, but it's a semiconductor that changes properties depending on temperature. So below 40 degrees, it acts as a conductor, not as a dielectric, and when you increase the temperature above 47 degrees Celsius, it completely behaves as a conductor. So it's kind of interesting. So this thing, if I were to look it from the top view, is just a big plate with those little patches. And we want to see, okay, can we use this material to detect gases? So methane or CO2 or something like that. So what we are doing is, okay, let's look at what will be the behavior when we just change temperature. So what you see here is the reflectivity, is the reflectivity of this antenna when you are passing a terahertz wave. So you can see the one over here is when it's behaving as a dielectric, and the one over here is when it's behaving as a conductor. So you can see in the electric, there's like this weird peak that we're not sure if that's the behavior or if there's something wrong with the simulation. But if this is true, then this will be a good frequency when we can detect any changes, because these kind of peaks, they're usually very sensitive to any variations of frequency, any changes in material properties. So this will be a candidate for us to explore. So the way you simulate this is by basically solving Maxwell equations at every single frequency. So you do a strip of all the frequencies between 200 gigahertz to 1,000 gigahertz.
So you're gonna put this program on Canvas for us, or
No.
We
do
have
you not have access?
students.
Do we? I don't remember.
I don't know. I need to.
This to things like this tend to be quite expensive,
Ah,
but.
I think we have,
Student
I think we have the student license for this one.
should look.
But if you are interested in learning this software, let me know. I think this could be an interesting research project. I think about this for you. I don't know. Anyway,
That's very cool.
any makes sense? Okay, so Monday we may do another separation of variables using spherical coordinates.
Oh, I just remembered, I can't make it.
I'm sick, man.
Future.
And there's a different method that we will start using, that we start working on. It's called mirror method. That can also be used to simplify some of these calculations. Or a different kind of problems. Any questions? Okay, you have this homework. Well, I'll put the homework for on Monday. So you can start working on this, but it's gonna be due until, not this Monday, will be due the 1st, November 1st, okay? So you still have some time for that one. Okay, sorry, this was